Welcome to lecture 9. Today we will continue with nucleophilic addition reactions of aldehydes and ketones. But before we continue, we will shortly revise what we learned in last lecture. Last lecture we discussed the structure and reactivity of aldehydes and ketones. And we now know that both aldehydes and ketones contain a carbonyl group. Aldehydes contain at least one hydrogen next to the carbon-oxygen double bond, whereas ketones contain two alkyl or aryl substituents. And we also learned that the carbon-oxygen double bond is short and strong, even stronger than the carbon-carbon double bond. Nevertheless, the carbon-oxygen double bond is reactive because the electrons in the carbon-oxygen double bond are polarized. As the oxygen has a higher electronegativity compared to the carbon, the electrons in this double bond are attracted towards the oxygen, and hence the carbon is partially positively charged, and nucleophiles will attack this carbon atom. Conversely, the partially negatively charged oxygen atom will react with electrophiles. And what did we also learn is that the carbonyl group has a resonance form, which is indicated here. So we can have partially positively charged carbon and a partially negatively charged oxygen atom, but we can also draw the resonance form in that way that we have a real positive charge on the carbon and a negative charge on the oxygen atom. And then we saw that aldehydes and ketones react in nucleophilic addition reactions. And the partially positively charged carbon atom will act as electrophilic site where the nucleophiles can attack. And here we learned that after the nucleophilic attack on this partially positively charged carbon atom, a so-called alkoxide ion is formed. And important to see is that the carbon in the carbonyl group is sp2 hybridized, whereas the carbon in this formed alkoxide ion is sp3 hybridized. And then we already discussed the reaction of aldehydes and ketones with hydrides, cyanides, and organometallics. And here is the reaction of a ketone with a hydride, and we can see that a secondary alcohol is formed. Conversely, if we now use, instead of a ketone, an aldehyde, we just replace at least one R group with a hydrogen, and we see that then a primary alcohol will be formed. The reaction of a ketone with cyanide yields cyanohydride. And again, you can just replace one R substituent with an hydrogen. Then you have the aldehyde instead of a ketone. And finally, we also discussed the reaction of ketones and aldehydes with organometallics. And here you can see the reaction with a Grignard reagent. And then if we use a ketone, a tertiary alcohol is formed, whereas if we use an aldehyde, a secondary alcohol is formed. Besides these nucleophilic addition reactions, we also had a look on the so-called Wittig reaction, and we learned that aldehydes and ketones react with phosphonium ylides to form alkenes in the so-called Wittig reaction. And for the Wittig reaction, we need a phosphonium ylide, and phosphonium ylides have a positively charged phosphorus atom and a neighboring negatively charged carbon atom. Now you can already think that this phosphonium ylide has several resonance forms, and one of these resonance forms has a carbon-phosphorus double bond, and this is called phosphorane. And phosphonium ylides are prepared in two steps from primary or secondary halogenoalkanes. The Wittig reaction starts with the reaction of the negatively charged carbon of the phosphonium ylide with the partially positively charged carbon of the carbonyl group. Hereby, betaine is formed. Then in the second step, the betaine further reacts and forms an unstable four-membered ring. And this ring is called oxaphosphatane. And finally, in the last step, the oxaphosphatane breaks to form an alkene and a triphenyl phosphenoxide. And the driving force of this reaction is the formation of a phosphorus-oxygen double bond. So in summary, the Wittig reaction replaces the oxygen atom of the carbonyl group with a Cr2 group. Today we will continue with the nucleophilic addition reactions of aldehydes and ketones. And first, we discuss the reactions with oxygen nucleophiles. The addition of water to aldehydes and ketones yields hydrates. In the first step, a lone pair of electrons of the oxygen atom of water attacks the partially positively charged carbon atom of the carbonyl group, and hereby an intermediate is formed which contains both a positive and a negative charge. Subsequently, this intermediate gets deprotonated by water, and hereby another intermediate is formed which now has a negative charge. Then in the last step, this negatively charged intermediate gets protonated by the hydronium ion, and the product, the hydrate, as well as water, is formed. Water is only a weak nucleophile, and therefore the addition of water to the carbonyl bond is quite slow. And in order to increase the reaction rate, usually acid catalysts are used. Hereby, the carbonyl group gets protonated in the first step, and this protonated carbonyl group is then a stronger electrophile. Afterwards, the nucleophilic attack of water on this protonated carbonyl group will proceed much faster compared to the addition without protonation. Then, in the next step, the positively charged intermediate gets deprotonated, and hereby the product, the hydride, is formed, and the acid catalyst is regenerated. Important to see is that all steps are reversible, and the catalyst does not affect the position of the equilibrium. The equilibrium is only determined by the stability of the carbonyl compound compared to the hydrate. And this in turn is determined by steric and electronic effects. The steric effects explain why aldehydes are usually hydrated to a greater extent than ketones. And you can see this here. If we compare the reaction of methanol with water with that of propanone with water, we can see that for methanol we have a hydration of 99.9%, whereas the hydration of propanone is only 0.2%. And the reason for this is the steric hindrance. You can see that in the hydrate, the steric hindrance is larger compared to the steric hindrance in the ketone, and therefore the equilibrium is shifted to the side of the ketone. Conversely, if we have an aldehyde, we only have the small hydrogen groups here, so the steric hindrance after introducing these hydroxide groups is less, therefore the equilibrium is on the side of the hydride. Another influence is the electronic effects of the substituents. For example, if we have a carbonyl compound which contains substituents with strong electron withdrawing effects, as this trichloroethanol, then the carbonyl compound gets destabilized, whereas the hydrate is not destabilized by the electron withdrawing effects of the substituents. Accordingly, the carbonyl compounds with substituents containing a strong electron withdrawing effect are hydrated to a great extent. Alcohols represent other oxygen nucleophiles, and the addition of an alcohol to the aldehyde or ketone yields hemiacetals or hemiketals. The overall reaction mechanism is depicted here. We start with an aldehyde or ketone and we add an alcohol, for example methanol. Then we use again an acid catalyst, and then we produce this molecule here. And if we started with an aldehyde, we end up with a so-called hemiacetal, whereas if we started with a ketone, we end up with a hemiketal. And hemi means that we produce half of a ketal or acetal. And a complete acetal would contain 2 oxygen R substituents, but we only generate 1 oxygen R substituent. And the reaction mechanism is exactly the same as we just saw for the addition of water. Again, as already for water, also alcohols are weak nucleophiles, and hence we always add an acid catalyst in order to increase the rate of the reaction. And as we just saw for the addition of water, all steps are reversible, and the position of the equilibrium is only dependent on the relative stability of the carbonyl compound and the hemiacetal. the formed hemiacetals react with a second equivalent of alcohol in the presence of an acid catalyst to form an acetal. And this reaction is a four-step reaction. In the first step, the hemiacetal is protonated, and hereby the hydroxide group is converted into a good leaving group. Then in the second step, water is eliminated and a pi bond is formed in this oxonium ion. This oxonium ion is a strong electrophile, and in the third step, the alcohol attacks the oxonium ion, and hereby the pi bond is broken. Finally, in the last step, the positively charged intermediate gets deprotonated, and the acetal is formed while the acid catalyst is regenerated. And also in this reaction, all steps are reversible. And to ensure the equilibrium lies on the side of the acetal, an excess of alcohol is usually added and also a dehydrating agent. This dehydrating agent removes water from the reaction mixture, and hereby the equilibrium is shifted to the acetal side. Moreover, usually anhydrous acids such as dry hydrochloric gas is used to provide the proton instead of aqueous acids, as aqueous acids would shift the equilibrium to the left side. And important to know is that acetals are protecting groups for aldehydes and ketones, as they do not react with bases, redox reagents, or nucleophiles. And the acetal protecting group is introduced by the reaction of an aldehyde or ketone with two equivalents of alcohol. If we have a look on this molecule, we can see that we have an aldehyde group and also a ketone group. If we then want to introduce this protecting group, we can see that only the aldehyde reacts with the two equivalents of alcohol. And the reason for this is that the reaction of a ketone is slower compared to the reaction of an aldehyde. Then we form the cyclic acetal, which acts as protecting group and will not react in the subsequent step with the Grignard reagent, while, in contrast, the carbonyl group of the ketone will react with the Grignard reagent. Then in the final step, the protecting group is converted back into the carbonyl group, and this step is a hydrolysis which is conducted in heat and with aqueous acid, and this step is also called the protecting step.